This is our second module in the trigonometry section. Module 16. We're going to look at the development of the trig functions, what they are, and how do we get them, and then connect that with the unit circle. So first we start off with the, before we get to the unit circle, we start with the triangle, which as we saw from, if you've done the measure triangle activity, you will see that there is a triangle embedded in each of the circles that we're going to look at. We'll look at that later. But the angle we're going to refer to is as theta, is this lower left angle. And in terms of this angle, the side opposite is the one over here. The side adjacent is going to be this side, and this is in reference to this particular angle. So if we were to talk about the angle at the top up here, the sides would be different, which we're calling opposite and adjacent. So these are relative to this angle, that this is adjacent. It's next to, it's touching the angle, right? The opposite is the opposite side of the angle. And then hypotenuse is the one that's always going to be on the longest side, because it's across from the right angle. So we're talking right angle trigonometry. So oftentimes people will use this word SOHCAHTOA to help remember the three main trig functions, and then with each of those functions has a reciprocal function. So that's how we get the 6. But these are the three main ones. If you remember these, the reciprocal functions sort of follow along. So we'll take a look at this. So SOHCAHTOA, the first part means that sine, which we abbreviate SIN. If you were to spell it, it's SINE. But the sine of an angle, and this time we're going to refer to theta, which is this particular angle here, we can arrive at it. It's just a function of the ratio of the sides. And as you see the O and the H, it's the ratio of the opposite over the hypotenuse. And we're going to do some activities where there'll actually be numbers here, and that's actually how we calculate what the sine is. And what you'll see is for a particular angle, the opposite and adjacent sides will always have the same ratio. Now, it all depends upon the length of the hypotenuse. The measurements may be different. But the other thing we're going to do is, as we look at the unit circle, the hypotenuse is the radius of that unit circle. So the hypotenuse will always be equal to 1 when we're doing that. And that makes things so much easier, because when you divide by 1, you're left with just the length of that opposite side. And again, you would have seen that. You will see that as you do the measuring triangles activity. So that's the SO part. CAH, C-A-H, stands for cosine, and we do that as C-O-S-I-N, cosine. And again, if we spell it out, we put a little E on the end. So it's something that goes with the sine. And again, we always plug in an angle value, and the cosine of an angle value is always equal to the adjacent over the hypotenuse. And it's just, that's what it's defined to be. Okay, we measure these things and we take its ratio, and that's what the cosine is. And then finally, TOA is standing for the tangent. And you'll see that, well, we'll abbreviate it, but that's how you write it out. We abbreviate it as tan of the angle is going to give us opposite over adjacent. And through this this lesson, you'll see all these different connections that we will make to these. Okay, along with each of these these three functions, they each have a reciprocal function. And a reciprocal function means we just do the ratio the other way around. So sine has a reciprocal function called cosecant. Cosecant, and we abbreviate CSC. And if we do that, it's simply the reciprocal. It's a hypotenuse divided by the opposite. Because sometimes it's useful to have these. So I'm going to put this as cosecant. And maybe through your study into calculus and such, you'll start seeing some connections between these words tangent and secant to other aspects of mathematics. For what we're doing, we're just using them as a function. And then cosine is matched up with something just called the secant, S-E-C. So the way it's sometimes hard to remember which one it goes with which, but if you just think of it, that the cos never match up. So cosine does not have cosecant, right? You can't have a co and a co. So sine goes with cosecant, cosine goes with just the secant. And that's going to give us the hypotenuse over the adjacent is that function. And again, we just use them. When we're asking for the secant, if we've got the triangle, we just take the hypotenuse divided by the adjacent. That is the answer. And then tangent has something called a cotangent, and we abbreviate that as C-O-T. So I guess maybe over here I'll put secant. And the cotangent, again, we should have some parentheses around these angles, is going to be adjacent over the opposite. Now, most calculators do not have functions for cosecant, secant, or cotangent. So for when we get to it, we'll show you how basically to calculate cotangent, you calculate 1 over tangent, and it'll give you it. That's why they're called reciprocal functions. Okay, so these guys pair out. All right. Oops, we're not done. How did it jump there? Okay. Let's see. Okay, here we are. Sorry about that. So this is just to kind of formalize it. And what I wanted to highlight, if the angle's in a different place, notice how the opposite and adjacent sides have changed now. If we are here, the opposite and adjacents are different sides. But so we take pay attention to where the angle is. Now, when we're doing it within the circle, we always use the angle down here because this is going to be our reference angle. This will be the x-axis. This would be the y-axis, right? And depending upon how it's sitting in there. But if we use this one, I just wanted to highlight these are the same features: SOHCAHTOA, sine, opposite over hypotenuse, cosine, adjacent over hypotenuse, and TOA, tangent, is opposite over adjacent. Okay. And what you see is we've got lines here that line up the sine with its reciprocal function, cosecant, cosine with its reciprocal function, cosecant, and tangent with its reciprocal function, cotangent. So they're just helper functions. Again, we could function just fine without these cosecant, secant, and cotangent as special functions, just going 1 over tangent, 1 over cosine, and 1 over sine. And in fact, that's kind of what your calculator will generally make you do. But we also have them here just as an easier way to reference things. Okay, so it's formalized. Now let's take a look at how we could actually calculate these trig functions given a circle of any size. And so this is not a unit circle. It has a radius, as we see here in the green, of 2.9 centimeters. It gives us a right triangle in here. So I'm going to kind of highlight that out there, because this is how we, kind of a funky looking triangle, but we've got 2.9 is, no, that's supposed to be our radius, is what that's referring to. And so up here, our hypotenuse is going to be 2.9. Okay, so that's kind of, maybe this picture is a little difficult to see from. The x-coordinate down here is from this point here, if we came straight down, so that's 2.67. And then the y value of this point, 1.13, is the side over here, which would be the opposite side. Okay, because this is the angle we're going to refer to as our theta, or our, we sometimes call it x, but we want to be careful because we're going to be thinking of this as a xy plane, and the x is actually going to be this distance here, right? This is the x coordinate, the red is the y coordinate. Okay, so how do we calculate the sine of this angle? That's going to be, so sine is opposite over hypotenuse, 1.13 over 2.19, or 2.9, sorry, I don't know where to get that one. And let's just kind of go through and list them all, and then we'll do the calculations all at one time. What is the cosine of theta? Well, cosine is ka, so ka toa is adjacent over hypotenuse. And tangent is toa opposite over adjacent. And just thinking of this in terms of a circle, we could also think of sine as being the y coordinate over the radius. Let's do this in red. So another way to think of this is it's y over the radius. Cosine is going to be the x over the radius, and tangent is going to be y over x, thinking of sort of slope, because that's sort of what a tangent is, right? And so we could calculate these, and all we do is here, 1.13 divided by 2.9. And that is the value of the sine of the angle. Now, a little bit later on, let's go ahead and do it in green. We're going to actually get the angles, and we'll see how the calculator could actually calculate this value from if we had the angle. 3897. I'll go to 4 decimal places. Cosine is going to be 2.67 divided by 2.9. So that's a 0.9207. And you'll notice that these values for sine and cosine are always going to be less than 1. We'll see the maximum they could be is 1, or in the minimum is -1. We'll follow that through with the unit circle. But we'll just finish up with tangent. Tangent is 1.13. Divided by 2.69. 2.67. Sorry, that's what, I guess I just need to be a little, oops, not that, I don't want that, I want this. If you can't read your own writing, it's time to take a writing class, I guess. 6-7. There we go. Let's go back to green. 0.4232. Okay. So that's how we can calculate those. We can also do the reciprocal functions. Now, there's two ways we could do it. Give myself enough room there. So I could do a cosecant. Remember, that's the reciprocal of sine. You could do it either as 2.9 divided by 1.13. I'm going to put that there. Or you could take the value we've got, do 1 over this. Now, it's a rounded value. It's probably, so whenever you round, you have a little bit of an error. And when you use something with a little bit of an error, you get more error, right? So I'm going to go ahead and do the 2.9, but I'm just showing you that, you know, reciprocal function, just take the reciprocal of this. That's really what the calculator does, except it carries more digits in there. Okay, and so we get 2. Oops. Back to here. We get 2.5664 into 4 decimal places. Okay, and I won't do all of these, but let's see the secant, which is the reciprocal of the cosine. So we take our cosine, and it's going to be 2.9 divided by 2.67. And then cotangent is the reciprocal of the tangent. So we can get that by 2.67 divided by 1.13. And again, I'll let you go ahead. You can calculate that use your calculator on that. And again, you could also get them from doing the reciprocal. In fact, let's just go ahead and do that for cosecant. Take 1 over 1 divided by 0.3897. We'll probably get close enough. Let's see, what do we get? We do get 2.5660. So you see, which would round up to 1. We're off here because of the rounding. Okay, so but if you were going maybe out to 2 decimal places, you'd be fine. 3 decimal places were fine. Okay, so that's with any circle. What we're going to do now is sort of simplify the process a bit. There we go. By using the unit circle. When we have a unit circle, what it's telling us is that the radius is equal to 1 unit, 1 centimeter, 1 something, but it's 1 length, right? It's 1 unit. And these are based on that. And so in this case, notice we have an angle that takes us into the second quadrant, right? Here's the first quadrant. Then we go to the second quadrant. Down here's our third quadrant. And over here's our fourth quadrant. And as we go around here, right, because x over here is positive, but x over here is negative, y up here is positive, y down here is negative. Basically, we get similar values, but what ends up happening is the sign confusing because we're talking about the sine as a function. The plus or minus in front, right, changes. So over here, x's are negative. So if we're ever in the second quadrant, we'll see that x's are negative, y's are positive. Okay. So how do we find these? Well, this gives us a triangle that is embedded in here. There's that one. There's the right triangle. And again, by going through the activity, measuring triangles, you'll see this. It's really giving us this interior angle. So this is what we call a reference angle. But this gives us, letting us know that that angle of the triangle is located in the second quadrant. So it gives us slightly different values than if this triangle was flipped over here, which if it were, we'd have the same numerical values, but the signs on them would just slightly change. We'd have the square root of 33 over 7, but it would be positive. And then the y coordinate would be exactly the same. Okay, so if we were actually just using what we call the reference angle, we get positive and positive. When we use this angle here, gets us over there, but notice we actually use the same reference angle as the first quadrant to be able to calculate it. If we, this is, so I'll call this theta r for reference angle. However, in this problem, we don't need to find out what theta is because we're given the values of x and y. X is the adjacent to this angle, right? Square root of 33 over 7. And we'll put it negative because that'll help us with our calculations. And the y coordinate is the opposite side. It's the y coordinate there. Okay, and since the hypotenuse is 1, when we go to find sine and cosine, we really just end up having, let's start with, well, we've started with sine, so in SOHCAHTOA, the sine of this angle, which we don't know what it is, if we know it's theta, is simply going to be opposite over hypotenuse, the hypotenuse 1. So really what it ends up being is just the y coordinate. So this is the power of using a unit circle, is we just, calculations are so easy. If we've got the y coordinate, we're done. Same thing with the cosine. It's just the x coordinate. So I'm going to put over here, this really just equals y. This really just equals x when we're dealing with the unit circle. Now, if it's not a unit circle, then the radius has some other value than 1. We have to remember to divide by the hypotenuse. Here we are dividing by the hypotenuse, but since it's 1, it doesn't change anything. Cosine is square root of 33 over 7. And tangent, this one we have to do a little bit of calculation for because it's going to be y over x. Notice, anyway, that's what it would have been. So y is 4/7 divided by negative square root of 33 over 7. And when you've got a fraction over a fraction, what we do is we're dividing the fractions. And when you divide fractions, you invert and multiply. So you flip the second one, take the reciprocal. So that's 4/7 times negative 7 over square root of 33. And what happens is you could do the division first. So you could take 7 divided by 7, which is 1. And our answer ends up being 4 over the square root of 33. And negative, actually, right? Negative 4 over the square root of 33. Now, there's something called rationalizing the denominator. So you might see this is multiplied. Some people would say you have to rationalize it. That was really before we had electronic calculators. Electronic calculators can handle this just fine. But in the old days, it was less accurate to try to calculate what this number actually was with the methods they had. So they would multiply by square root of 33 over the square root of 33. And so you'll see this in the notes, possibly as -4 square root of 33. Denominator square root of 33 times square root of 33, which is positive. It just becomes 33, right? Square roots sort of cancel each other out. So this is another way to write it. I like just leaving it this way because in our modern world, we can deal with it. Okay. So the cosecant, this is where it becomes easier. So remember, cosecant is the reciprocal of sine. So you just take the reciprocal, 7/4. Secant is the reciprocal of cosine. I guess I should have parentheses here. They don't always do that though, do they? You just take the reciprocal, so you flip it, and that's 7 over square root of 33. And we still have the negative on there. And then for cotangent, once we have the tangent, we just take its reciprocal. And so that's why I like the one I have in red. I'm going to leave it that way. Square root of 33 over 4, and it's negative. Okay, so keep the signs right. And see, if you did this, then you would flip it, and then you'd have to do the rationalizing again. But anyway, that's how we can get the 6 different functions based on just, with the unit circle, just knowing the coordinates of the point on the circle at that angle. Okay, so several of the homework problems have you do that. Okay. Now let's take a look at how we can use the unit circle. Here's a copy of one. I do have a video in the session in the course on how to create this. We talked about it in the measure triangles activity, so these are where it is. The problem is 13 pi over 6. As I go around, I don't find that here. I find 11 pi over 6. So where is it? Well, let's not deal with that right now. We'll come back to it. But what if I, let's take an easier one. What if I wanted to know what the cosine of pi over 3 is? Well, cosine, remember, since this is a unit circle, and I know that because from here to here is 1, all I need to do is take the x-coordinate of pi over 3. So cosine of pi over 3 is equal to 1/2. Just reading it off of here. Now let's return to where is 13 pi over 6. The previous lesson we talked about coterminal angles. And what you might have recognized is this is 11 pi over 6. This is another pi over 6. So this is actually 12 pi over 6. You know, 2 pi is, right, 12 pi over 6, because 12 divided by 6 is 2. It's another way to write 2 pi. So 13 pi over 6 must be 1 more. So this pi over 6 must also be 13 pi over 6. All it is when it's 13 pi over 6, it means we went around the circle and then a little bit more. The values are going to be the same. However, 13 pi over 6 is a different animal than pi over 6. Especially in sort of engineering problems, you might be dealing with a spring, so it's been wound up one extra turn over pi over 6. So it could give us some different values depending upon the situation. However, the cosine of 13 pi over 6 is actually going to be the same as finding the cosine of pi over 6. So just cosine of 13 pi over 6 is equal to the cosine of pi over 6. And again, all we have to do is come here, take the x-coordinate, and that's going to be square root of 3 over 2. Okay, so that's how we can use the unit circle to find cosines, sines. Remember, sine is going to be the y-coordinate. Tangent we have to calculate because that's going to be the y-coordinate over the x-coordinate, but we could do all of those just taking off the point, as we did with that last one. Pythagorean trig identities. Now, when we have a right triangle, and we're going to do it from a unit circle, so we'll say the hypotenuse is 1. Remember, this would be x and this would be y. The Pythagorean theorem says that if you could take x squared plus y squared, you'll be equal to the hypotenuse squared, which is 1 squared, which is just 1. So as we go into our trig identities, remember, from the unit, when we have the unit circle, the x coordinate is what we define the cosine to be, cosine of the angle. The y coordinate is what we define the sine to be. And so what that shows us, just coming from the side squared plus the other side squared gives us the hypotenuse squared, that we get this Pythagorean identity that if we take cosine theta and we square it, and we add to it the sine theta, and we square that, that will equal 1, or 1 squared, because we're using a unit circle. Now I've got it written this way, the way they end up writing cosines, they put the square really on here. But when you go to calculate cosine squared in your calculator, you can't do this. You can't go, let's do cosine squared. Oh, it doesn't look right, and it's not right. It's going to mess up. If you want to do something with a cosine squared, let's say cosine of, let's say I'm in radians, cosine of pi, this little pi over 2, and you want to square it, you would do it this way, and then at the end square it. Now, cosine of pi over 2, that's probably a poor choice because it's 0, and when you square 0, you get 0. But anyway, you've got to square it from the outside. But what you will see written is, you'll see it written as cosine squared theta, okay, plus sine squared theta equals 1. And we're going to use this a little bit later in the course. It's something that comes up quite often and gives us various identities. And one of the identities it gives us, we could subtract sine from both sides, right? And so that'll give us, if you subtract sine from both sides, you get that cosine squared theta equals 1 minus sine squared theta. You can also, if we take this original, and then also we could solve it for sine, and okay, so I guess I'll do that one, because a lot of times these are ones we will use. We'll substitute them down the road. Don't worry too much about it right now, but just know that these exist. And sometimes we do this as we introduce you to something. We don't have you work on it right away, but we're introducing it to you, so it's part of your memory. Okay, and there's two others where, so we could take this equation, we could divide it by sine squared, and that's in the notes, so take a look at that, and that'll give us another one. And we could divide it by cosine squared, and that gives us another identity. And I'm just going to put them here as these additional identities. We're going to use these later. We'll redevelop them as we get there, but as for now, we're just kind of introducing them as something that exists, okay, coming from the Pythagorean theorem. So how do we use a calculator to find values of trig functions? Well, I just showed you one way, but let's take it, what if I had degrees? So what if I wanted to find the sine of 40 degrees? Now that's not one of our special angles. The first thing we want to recognize is, notice up here on my TI-84 calculator, it's telling me I'm in radian mode. Calculators have two modes because we measure triangles, or triangles. We measure angles in either degrees or radians. We have to know which one we're using. We have to tell the calculator, since we're using degrees, we have to switch it to degrees. And that's done by clicking on the mode button. And we notice if we come down a little bit, there's radians. If we want degrees, we arrow over, we hit enter, and now we're in degree mode. The way I get back, I don't know if it's the only way, but I'll go to this quit. So I go second, quit, takes me back to the main screen. And now you see up here, I'm in degree mode. Be careful with this. Whenever you're doing a calculation, you've got to be in the right mode. If we would have done this calculation while we were in radian mode, it would have read this as 40 radians, not 40 degrees. Okay, so that's, it'll all make more sense as you make a few mistakes on it. You wait, how am I getting the wrong answer? Well, they gave you radians and you were in degrees, or they gave you degrees and you were in radians. So we're good here. So it's simply equal to 0.6428, again, going to 4 decimal places. Again, what if I wanted to find the cosecant of a value? And I guess we'll go ahead and go with 40 degrees. There is no function in here for cosecant. It's not sine to the minus 1. We're going to talk about that later. That's an inverse sine. So what we have to do, though, is we have to do 1 divided by sine of 40. And that will give us the reciprocal. So that's how we calculate a cosecant. Okay, and that's going to be 1.5557. Okay, and if we want to switch over, maybe we want the tangent of pi over 5. Well, there's no degree marker here, so this is definitely in radians. We're going to want to switch back to radian mode. Go down, select radian, second, quit, back here, and now I can do the tangent. The pi is this little shifted button here. Divided by 5. And there's my value. Four decimal places. Okay, so we could use the calculator to do that. And that's helpful if we have an applied problem, such as this. We're going to use an equation to calculate a value. So we've got this formula here. It's got a sign in here. So it's something based on the angle, and that's what we'll find out is when we do these problems, anything involving an angle will involve some trigonometry. And it's telling us the horizontal distance d, so this d is a distance of an object. If we launch it at angle A, so it's like it's getting sent into the sky at some sort of an angle, or angle theta. Why did I say A? I don't know. Theta, with an initial velocity of d naught, v0, which is velocity is speed and direction. Okay. We have this following formula. They give us these values. They give us g, which is actually a gravitational constant. V naught is going to be the speed, and it's in meters per second. And here's our angle measure. So to calculate the distance, actually, doesn't look like there's a question here. I just copied this out of something else. So, but they want us to calculate it. We're going to use this formula. What is V naught? V naught is 90. And notice we square it. So this is going to be 90 squared times the sine of 2 theta. So it's going to be 2 times 0.78. Notice they tell us it's radians, so we want to make sure we're in radians. And then we divide this whole thing by g, which is 9.8. Okay. So coming over to our calculator, let's just kind of clear it out so it's a little bit better. I'm going to show you a trick with this one, a little trick, is if the f1 function, if I go to alpha f1, so I hit this, there is, it'll actually give me a fraction template. Let me call it a numerator denominator thing. So I'm going to enter that in because I have a fraction here, and this just helps make sure that everything, the order of calculations is going to go right. So there's 90 squared, arrow not all the way down here. I'm then going to do multiply. I might not need to do that. Sometimes when you write things next to each other, it knows to multiply, but I'm going to do that. And I'm going to go do 2 times 0.78. You could do 0.78, but 0.78 will work. Close that off, and then come down to the denominator, and we have 9.8. Make sure we're in radians. If we weren't, we'd want to switch back. Again, always do that check whenever you're doing this, because if we're in degree mode, it'll give us an answer, but it'll be incorrect because this is not degrees. Okay, and then we just hit enter. So it's telling us that the distance traveled was 826.48. I don't know how many, and that's going to be meters, because that's the units we're using, meters per second. Gravity is being measured in meters, so that's how we can use trigonometry to actually apply problems. Okay. And you could see now, you could play with this a little bit. If we made it a bigger angle, would it go further or less? Probably, I guess probably less, but I don't know. It just depends on what that angle. If we did a smaller angle, and that's how we can judge how far do we need it to travel. Okay. So there's this activity here. It kind of, again, it's going to get us a little bit ahead of what we're doing. But this is going to create a cosine graph from the unit circle. So there's a little, so watch as it comes around, as theta gets bigger, we get the x coordinate. That's what's getting measured here. And then it's showing it being drawn out on a different set of axes. This axis has the x-axis is the angle. The y, I guess I'll write that in there. The y value is cosine of x, we'll put it. Down here, x is the angle, right? X is the angle measurement, and we see this sort of thing. So we're going to do more later on with graphs, but this is how it's developed. It's actually using a separate set of axes, where h is the cosine of theta, cosine of x. The x-axis is the angle being measured. When we're on using the unit circle, x is just a measurement, and y is just a measurement, right? It's a distance. But here, y is not a measurement, it's the cosine of the angle. And x is not a linear measure, it's a measure of what the angle is. So we're making these kind of connections. So again, something to kind of look forward to as we get more into doing graphs. And that will conclude our discussion for this module. So start working on the learning activities for this module. And remember, we have various resources to get assistance as you go through. There's online tutoring, there's instructor office hours, and as well as working with peers in the discussion forums.